Good day. This is one of the most important set of notes we're going to have in this course. We're looking at Le Chatelier's principle, and it's going to apply to every section that remains. So we have a chemical system that's equilibrium, and we expose it to a stress. Processes are going to occur to oppose that stress. Stresses are changes in concentration of reactants or products. It can be a change in temperature, it can be a change in pressure, especially if we have a gaseous system. You should have watched a brief video about KQ. We'll do the math of it in much more detail when we do the math part of this section. But at this point, you just have to understand KQ is the ratio of products to reactants. So if we have a large value of KQ, it means we have more products than reactants. And a small value of KQ means we're going to have more reactants than products. If we had a reaction go to completion, in theory, our KQ should be infinity. And if we had no reaction, our KQ should equal 0. So let's look at the effect of concentration. Increase in the concentration of reactant. Well, we want to use up some of that reactant so the equilibrium shifts right. As it shifts to right, it uses up some of the other reactants, so their concentration goes down, and we make more products, so the product concentration goes up. Well, we look at this and we say whatever we had here, it has to be the opposite if we decrease the concentration. So instead of shifting right, it shifts left. Instead of increasing concentration products, it decreases concentration products. We use up those products to regenerate some of the reactants. And again, we go to opposite land. So now if we're increasing the concentration of product, the equilibrium shifts left to use up some of that product, and the reactants concentration will go up, and the concentration of other products is going to go down as the shift occurs. And once again, we get opposite land. So increase in concentration of product shifted left, so decrease in concentration of product shifts it right. That means we're going to make more product and we're going to use up some of the reactants. So let's look at an example here. If I increase the HI, things that could be asked, which way does the equilibrium go? Well, if this goes up, the equilibrium is going to go right to replace it. So I know it's shifting right. The HI concentration will go down after as the shift occurs, and the H2 and I2 will go up. If I do the opposite, if I drop the HI, if that's going down, the H2 and I concentrations will go down because they're shifting left to replace the HI, and the HI will come up somewhat. Increase in the H2 is going to drive it to the left. This has gone up, we got to go, and we're going to make more HI. We're going to use up some of the I2, and the H2 will drop down somewhat after the stress is imposed. And decreasing the H2 has to have the opposite effect. If we decrease the H2, the equilibrium comes to the right, some of the HI is used up, and we make some more H2 and we make some more I2. Pressure. If the stress is pressure change, there's no effect on the KQ value. Increase in pressure is going to favor the side that has fewer moles of gas according to coefficients, and that's because fewer moles of gas don't want to take up as much space. If we do the opposite, if we decrease the pressure by making the volume bigger, equilibrium is going to shift to the side that has more moles of gas according to coefficients. So let's do an example here. So increase in volumes, decrease in pressure, decrease volume, increase in pressure. What was that? Hopefully it comes in nicely. Adding inert gas does not cause a shift, and we'll talk about that in another place in more detail. Let's look at an example, get straight to it. So if I increase the pressure, what I see is I have 2 moles of gas, according to coefficients here. I have 1 mole of gas according to coefficients here. 1 mole of gas can better handle confinement, so the equilibrium is going to shift to the right. So I'll get more N2O4 and less NO2. Decreasing pressure has to have the opposite effect. That's making the volume bigger. This can better fill it. Equilibrium is going to shift to the left to go to the side with more moles of gas. Temperature. If we change the temperature, we get a new value of KQ. Increase in temperature favors endothermic reaction. You can think of it according to a P graph or according to treating energy like a material. Decrease in temperature favors exothermic reaction. So an increase in temperature, we want to use up that energy, and that's why we go the endothermic way. Decrease in temperature, we're going to replace the energy, and that's why it goes in the exothermic way to generate some energy. There's a random picture. That's a border collie. Okay, so let's look at our first stress. If I increase the temperature, we can think of it as, oh, this has gone up, that's like a reactant, and the equilibrium is going to go to the right. We're going to use up some HI, and we're going to increase the H2 and I2. For this equilibrium decrease in temperature, it's got to go left. It comes this way to replace that energy. Catalyst has no effect on the equilibrium constant. You get to equilibrium faster, but there's no effect on the position of equilibrium. Simply get there faster. That's just the beautiful Bruins from 2011. Nice corn maze. Graphing concentrations. That's in another video that you'll watch very shortly. So don't worry about that at this point. That's where we'll end this video.